Okay, great way to start. Okay, welcome everyone. Now we have much more people in comparison with the first lecture. So during the first lecture, we actually, come on. Yeah, we talk about the history and current applications of AI. So okay, give me a sec, I will run it again. Now it's working. So I will start from the scratch because we are recording. So welcome everyone for the second lecture of this class, Machine Learning Techniques in Structural Mechanics. And if you remember from the first lecture, we discussed the history and current applications of AI. We learned that AI has a long history dated back to actually 1915s and 1957. So it may sound a little bit strange, but actually that's true. The concept of AI was formulated approximately after Second World War II. Oh, World War II, sorry. We know that AI survived several winters. It's basically lack of interests or lack of funding due to actually overhyped expectations. We know that right now there is a real boom in AI development because right now everyone is trying to implement AI and put AI into everywhere. Now, and actually during the last lecture, I showed how many scientific and engineering tasks will benefit from AI or already have these benefits. Now we actually know also that public can use AI achievements via easy-to-use frameworks. So TensorFlow, PyTorch, that we will use during this class, TensorFlow in particular, that's really, really easy to enter frameworks and very easy to implement your basically first neural network and then be happy with that. And if you are interested, just continue. So this class actually exactly about that, how to use this easy to enter frameworks. But also, we actually learned from the last lecture that you need to be very, very careful with AI in machine learning because I introduced this thing, GIGO. So if you remember what does it mean, it's basically garbage in, garbage out. So we actually demonstrated some examples of very bad AI and bad machine learning when it went absolutely as in planned. So be careful when you implement AI and ML. And also, last week we had a setup session, and we installed Python, NumPy, and TensorFlow with the help of Gerrit Felsch. So I hope that everyone right now has these frameworks installed. So we actually run some tests, and we did very, very brief introduction in Python in general. So this week, we would like to have this proficiency test on the Python programming, and not only on programming, basically on your ability to Google information and to basically search for the right answers. So right now, I think it's quite useless, to be honest, to do the classical tests when you have no connection to the internet and try to do something on a piece of paper. I think it's a very old approach. Now we really want you to basically demonstrate how well you are able to Google, able to understand what you're actually Googling, and implement some very simple Python tasks. So this Thursday, we will have this proficiency test. Bring your laptop. Please attend, otherwise we will assume that you are experts, and it may play not a good. It may have quite not good consequences for you if we assume that you're experts and you are not experts. So now, this week, I will talk about foundation of ML. We will talk about the basically artificial neurons, and we will build our first neural network. And we would like to do that not just from mathematical point of view. We will actually introduce your problem from structural mechanics. And together, we first solve it manually. And then we will implement very simple neural network that actually can do that for us. So first of all, neural networks. Why neural? So what you can see here, it's basically image of the neuron that we have in our brain, and each neuron has some synapses and dendrites. It's inputs of the signal, and then something happens inside of the neuron. So there is something happens with these inputs, and at the end we have this output axon here, and basically that three components of neuron. It's like neuron itself, its input, and its output. So neuron accepts electrical signals from dendrites, process them. We will put that a little bit in quotation marks, and outputs the resulting signal to the next neuron. So can we create something similar from the point of view of computation? Can we create artificial neurons? And yes, that's actually what was proposed, I think, in 1950s, 1960s. This example of artificial neuron is also called perceptrons, but to be honest, it's not exactly correct to call this perceptrons, and we will see later why. So basically the concept that we have this node that is called in neural networks, and we have some inputs similar to the dendrites of our real neurons, and then we have output Y. Very important part of all these things is that these inputs have different weights. So one of them can be very, very important, for instance, for our neurons, and another, nah. So kind of another maybe signal can be completely ignored. And actually there is a very nice, okay, an output in this case is created as a linear combination of our inputs and our weights. And as you can see again, as already mentioned, if let's say W1, the weight of this neuron is very high, you will have a dominant role of this first term. So, and if let's say W2 is very, very small, then therefore the input from X2 will be completely ignored. So this is a very basic concept. And I think we have a nice YouTube video that's showing us that actually this is a neurons in a, I think it's a petri dish, and you see how they're not only growing and connecting more and more, but also how the thickness of these networks is changing. It's basically what's happening during the basically living. The weights of neurons, they're basically their amplitude of the signals that are propagating through this dendrites is changing. So it's very, very good equivalence between what's happening actually here and what will happen when we will train neural network. So we will see that maybe this class, maybe the next lecture, so that we're actually doing quite similar things in computation. So that's really, really nice image. It was a very nice neuron time-lapse. But now I would like to ask you a question. Let's imagine that we have only X1. So we have a very simple system when we have basically only one input X1. Then we have this weight V1. And at the end, we have Y. So according to the formula that you see at the bottom, what would be in this case Y equal to? Yeah, exactly. So if X1, let's say, we just say that it's X, what it will represent if I plot Y versus X? What we will see? So, okay, if let's say W1 will be equal to, let me change the color. So if W1 will be equal to 1, what we will see? Line what under which angle? 45 degrees, of course, again, super obvious. So this is equal to, let's say, 1. So if we say W1 equal to 2, what we will see? Yeah, we will see in this case a little bit more inclined one, something like that. W1 equal to 2. So now, if I will go through all W's, what objects would I have? So if I will just sweep W1 from minus infinity to plus infinity, I will get all straight lines just passing through the origin, right? So basically we'll have something like that, something like, okay, they're straight lines, so believe me. What we are missing? Do we describe all lines using this particular equation? Which lines we are missing? What do you mean in between? But why? No. Why like, it's not about the points, because actually if you just put all lines through the origin, you will intersect with all possible points. X is no Y. I try to put W1 equal to 0, and I have quite nice X's. So I think that actually what we are missing, we are clearly missing something like that. There is no way to represent this particular line using W1 multiplied by X, right? How can I actually amend my equation in order to take into account this line? Oh, we can really, what we can do, we can say, okay, plus B. So base, come again? Yeah, it will be, in this case, it will be y-intercepting minus B. But in general, using this approach, yeah, we actually can get what we want. So, and that's exactly what we are missing. We are missing so-called bias B. And as you can see here, we add the bias to this equation. And now we can actually cover whole our space. This is quite important thing. Okay? And bias is important. So in many cases, bias is actually formulated as we use W0 for one specific reason. In order not to write this linear combination in a very like each term after the term, we usually can see this particular way to do that. So we write that our output y is equal to, you see it's bold, this is actually vector of inputs. So we have x1, x2, x3, and so on. So now what we actually have, so basically our vector x, let me again switch to something like black. So our vector x will be x1, x2, and so on. So our vector w will be in this case 1, v2, and so on. Question why I need to do transposed here. Yeah, basically to be able to multiply. So we cannot multiply row by row. So we can either row by column or column by row, depending on the rules. So, and what type of the object W0 in this case bias? Is it vector? It's a scalar, yes. And you basically add this W0. So this is called vector form, and you will see a lot of this form into literature. So it's a basic thing that happens in neural networks. And now we're actually ready to do one thing associated with mechanics. I hope that all you're familiar from the school, at least to the systems of springs. So if you have a spring, let us make it a little bit, let's make it a little bit harder first. Are you familiar with basically this equation? Who is not familiar? Tell me. Perfect. What's the name of this equation? Hooke's law. Yeah, again, this is a Hooke's law, and if you're all familiar with it, we will use that. So another way to do it in school terms, we can write that force of the spring is equal to stiffness of the springs multiplied by displacement. So, but we will use this one. So let's now remember, it will be exercise for you. If I have two springs, let's do them like that. That will be E1, it will be E2, and I apply epsilon, let's say, applied. What would be total Young modulus of this system? How can I find epsilon total? We don't have A3. Oh, right now, again, we don't look at the left picture. We right now simplified. We just basically have two springs in series, so 1 by 1. So what would be the in this case E total here, according to you? Go. Yeah, exactly. So let's, that's absolutely right. Let me just briefly show why. I think this actually quite, from mechanical point of view, it's quite important. Think it's the following. If we have our epsilon, therefore we have some sigma, so we can write the sigma is x equal to epsilon total multiplied by this applied epsilon, right? So Since we have a springs that in series, that means that sigma, the stresses in the first and the second springs will be the same. So therefore, what we can actually write, we can write that epsilon 1, it's basically elongation, it's basically the strain in the spring number 1 will be equal to sigma divided by E1, right? We inverse it, and in this case, epsilon 2 would be sigma divided by epsilon 2, and from here you kind of obviously see that epsilon A is actually epsilon 1 plus epsilon 2, like basically total thing, and from here we can easily see that epsilon total would be, I will write it in more canonical form, something like that, okay? So that's basic mechanics. So let me also in this case for you try to derive what will happen if we have the system when we have spring like that and spring like that. And now for simplicity, we actually will apply sigma A. What would be the total stiffness if this one is E1 and this one is E2? So I'm right again. That's correct. Let me just show you again. So from here, what we have the sigma epsilon is E total multiplied by epsilon, and epsilon actually the same in both of the springs because they're in parallel. So therefore, we actually can see that sigma A is also epsilon 1 plus epsilon 2. I have no idea what's happening, why it's happening. So, and therefore, we clearly see that epsilon total is equal to epsilon 1 plus epsilon 2. Okay? Now I am asking you a question about the system on the left. So now we imagine that we have a system where we have one blue spring and two red springs. And I'm actually asking you, can we search for the total stiffness? You see here, y is equal to ET. ET is the total stiffness as a linear combination of x1 and x2. So can we do that? We can do it easily because if x2 is Young modulus of red spring, so what would be the total stiffness here? Half, exactly. So that would be ER divided by 2, and on the left we will have basically blue spring, right? And the total stiffness in this case would be half of ER plus AB. And that's exactly what we have here, okay? That's interesting because I actually... Okay, well, this one should be orange, of course. So we actually see right now that we can find y as a linear combination of x1 and x2, right? So with the two different weights. So what weights do we have right now? Weight W1 is equal to 1, and weight W2 is equal to 0.5. And now we can actually, what we can do, we can just basically plot this equation. So here we have this nice contour plot, x1 on the x-axis, x2 on the y-axis, and the color will represent the total stiffness. And we actually can easily see that it goes from 0 to 15 in the corner, when basically we have the stiffness of red equal to 10, and stiffness of, like, Young modulus of red equals to 10, and Young modulus of blue equal to 10. Then total is not 20, it's 15 because we have them in series. So that's quite easy thing, and we can easily predict that. But now I would like to ask you a little bit different question. So let's assume that we are now not searching for the total stiffness, but we would like to analyze if our system will fail or not if we apply 10% elongation. So we apply 10% elongation, and now we don't care about the total stiffness, we care about local stresses inside of the springs. Because we know that if our stress exceeds some critical value, we may have either ductile or brittle failure. So I would like to avoid that, right? So now I will ask a question. So we have this new variable, y prime, and I would like it to be equal 1 if our system is intact, if nothing is failed, and I would like it to be equal to 0 if our system failed. And this is not kind of just out of the blue example, because those of you who attended the course of micromechanics remember this slide. It's one of the very famous engineering disaster with quite high death toll, happened in Kansas City in a hotel. And basically what happened, this particular hotel had two bridges, like you see them on the left in rendering, one bridge and another bridge on the top. And by design, they had to be connected in this particular way. So architects and engineers calculated that this particular form, this particular architecture, and when the engineers and builders start to erect this particular hotel, they had a problem, because for this design you had to find a very, very long rods with actually with a screw on that, basically the rods that you can also tie it with the screws. So, and that was a problem from the manufacturing point of view. So one smart, not so smart, but yeah, engineer decided, okay, why should we care about the long screws if we can actually split it by 2 and just assemble this particular structure? It seems absolutely the same. Really nothing is changing, according to him at least. But what actually happened, if you do a very easy and very simple analysis of the forces, you will see that in this particular nut, you have a twice, the force is twice as high as actually in the design number 1. So of course, even with the safety factor, so high force was not accounted for, and during one event when we have a lot of people on these bridges, basically everything collapsed. And you actually see this is image after this bridge collapse. You have no bridge here, basically, and it was one of the most important, from some point of view, engineering disaster that changed the building code in US quite a lot. So, and you actually see that our problem that we are considering here, it's quite similar from some point of view. So we care not about the total stiffness of the system. We are caring about if our system is safe or not. So now I'm asking you, so we have this particular equation. We would like to represent it in a similar way that we did basically a couple of slides ago. And simply, if I do, let me do calculations, because I think that's calculations are important. So if we have epsilon equal to 10%, let's say this is epsilon applied, right? So in this case, the sigma in the blue spring, of course, would be equal to epsilon E blue multiplied by this applied epsilon, right? And therefore, we want epsilon sigma critical, that we will consider the basically critical stress when this spring fails, need to be larger than our sigma there. Okay, so from here we can easily see that that means that epsilon. Oh, what was that? We can easily see that EB need to be less than sigma critical divided by. Okay. And for the second one, we actually know that sigma inside of this one would be half. So we actually know that sigma in the red one would be and therefore we actually it need to be smaller than right, sorry. So do you understand why we have these equations from mechanics? Let me just check that I did assign correctly, but I'm pretty sure I did everything as it should. Yep, exactly. So again, this is very, very simple mechanical consideration. I will not go into details. So now if we know that epsilon that we applied, let's say 10%, so basically 0.1, So let's assume that our sigma critical is equal to 0.25 megapascals, right? Again, or to be completely correct, we're actually working in, whoa, what was that? We're working in this dimensionless system, so we don't need to put megapascals there, but it's like something equivalent to megapascals. So now, if I draw the plot x1, x2, what will I have? I don't know how to do that. We actually have this region that is green when our value of I prime should be equal to 1, because both of these equations are satisfied. So x1 is less than 2.5 and x2 is less than 5, and therefore our system is intact and safe. If we in the blue region here, that means that we already have failure of one of the springs and our bridges will collapse. And now we cannot predict that. We cannot we cannot find the weights W1 and W2 in order to predict this I prime. Are you agree with that? Because this is kind of system that is quite nasty. So we cannot find W1 and W2 values in order to describe this picture in contrast with the previous plot that we did for the stiffnesses. And now I will ask you a question. What would you suggest me to do? What would be your solution for this particular problem? Any ideas? Any ideas? How can I improve my system of equations, let's say, or this particular equation, linear combination, in order to be at least able to do something similar to this particular plot? Any ideas? What I need to do? Yeah, that's right. So this system, I didn't want to pronounce this word, but yes, it's nonlinear. So we are trying to, using linear combination, describe nonlinear function. And yeah, you will not succeed if you will try to do that. So therefore, it's crucial to introduce nonlinearity into the model. So basically, in some cases, you can avoid that, but it's so rare, so that all our modern neural networks will require this nonlinearity. And how does it look like? It's very easy to see here. We have our neuron. We basically have x1, x2, x3 as inputs. We then combine them with the weight vector, add bias, don't forget about bias, and get our output y. So how we modify it? We now have this additional node. It's actually living inside of this green one, but I just separate it. And you basically first calculate this particular linear combination, and then apply some function on the top of that in order to break linearity, in order to create this non-linearity that, as we see right now, is crucial. So, and at the end, our output looks like this function of some intermediate variable z, and z is our old variable that we use as a linear combination. Okay? And now, my question is, can you name very nonlinear function? So right now we have quite arbitrary choice for this g function. So any ideas of very nonlinear function? Sine is quite linear because you can do this Taylor expansion, and yeah, it's not definitely it's non-linear, but it's not nasty. Like it's not nasty. You can really work with the sine. So something really nasty. Any suggestions of non-linear function? Exponential is also very nice and smooth. I would like something very like non-smooth, even non-continuous or something like that. Any ideas? Exactly. Step function is one of the like the nastiest functions probably. So this is exactly what we have here, we have this step function. Basically, if our x is higher than 0, we have the 1. If we lower than 0, we have 0. And in 0, we have something weird. And this is very, very nasty functions. But actually, it's quite bad for a couple of reasons. And you will see basically on the next slide why. But I can actually hint it. First of all, you have a problem at 0 because it's not actually well defined there. And second of all, what will happen if you take derivative of this function? What will be derivative on the left side of 0? What is derivative of this function? Like in -1? 0. Yes. What's the derivative of the function in the point 1? 0 as well. So this function is actually quite boring because it's really zero derivative everywhere except probably this weird point 0. So therefore, in machine learning, we more often see these two functions. This is called sigmoid function, and this is called hyperbolic tangent function. And actually, we see them here again. So this is our good friend Heaviside or step function. Basically, it's 0 if we're below 0, and it's 1 if we higher than 0. It doesn't really matter where you put this equal sign. It really doesn't matter. This function looks a little bit weird. It actually uses exponent there, and it's ranging from 0 to 1. And in 0, it's exactly 0.5. This is a very common function in machine learning. This is another super often used function. It's called hyperbolic tangent. And what's the difference between this particular function and sigmoid is that it goes from -1 to 1. And also it has a little bit better slope here, a little bit. It has different slope in comparison with sigmoid. So, but on the right, you see another family of the functions that are very, very popular. This is called ReLU function. It stands for rectified linear unit. So basically, this function is y equal to x on the right. So it's 45-degree line, and on the left we have 0. So because we have the same problem with this divergence here, not divergence, sorry, with derivative here, it's 0 everywhere. There is another function that basically modification of our ReLU function. It's called leaky ReLU. So on the right, it's absolutely the same. And on the left, we have a small slope. It actually helps a lot in the process of backpropagation that we will study next lessons. And finally, there is more exotic function. I think it's called exponential linear unit. And again, on the right, it's still linear unit. On the left, you have actually some exponential function. And as you can see here, in comparison with, for instance, leaky ReLU that has a constant, it's still not 0, but it's still constant derivative. We have non-constant derivative if we move in the negative values of x. So if you look at implementation, if you look how we use these functions when we build very simple neural networks, usually you can directly put them into the definition of the layer. I will talk about that a little bit later. So you say an activation is ReLU, activation is ReLU, and activation is sigmoid for the last. Do you have any idea why at the last we have a sigmoid and not ReLU? Okay, well, let's say we have a you don't know about classification problem. Again, this is quite common. You very rarely use a ReLU function at the end because it can infinitely grow. And usually in your task in machine learning, you don't want to have the value of 10. Let's say you very often want to value between, let's say, -1 and 1 or between 0 and 1. So that's why sigmoid is very, very popular function for the last output layer, and we'll talk about that basically on the next slide. And this is the next slide. So of course, when we discussed only one neuron, it's quite boring. We still can predict something, yes, but it's still very, very boring. So usually when you create a neural networks, you combine multiple layers and multiple nodes in each layer. So this is called input layer. This is basically our output layer. And these particular things between them, right now I use only one layer between them, but you can have 2, 3, multiple of them. They are called hidden layers. And mathematical operations basically are very, very simple. So let's take a look at the neuron number let's take a look. Basically, let's take a look here. Right, this neuron is neuron in the second layer. Usually, what you have on the in the superscript, it's a number of the layers. So you see 1, 2, 3, and it has 2 inputs from the previous layer. Okay, and therefore, in order to find the value here, what you are doing, you take the weight of this particular. Let me in this case of this particular connection, and it would be the connection W1, 2, 2, multiplied by the value of this. Okay, of this one. Then it's basically the first component of the sum. Then what you take a look at this one, and it will have the weight that you can describe as W2, 2, 2, multiplied by this value, so it will actually go into the sum, and add bias. So it's usually a very convoluted way to write, but what you need to understand, so basically if we look at this particular node, this node is associated with the weights of this node. So basically all these inputs are associated with this particular layers. That's why you have this 2 here, 2 here, and 2 here. That's basically what you're computing. And you multiply it by some values from the first layer. And in this case, this sum that you have here, it's sum over all inputs that you have in a previous layer. It's again, I find this particular way to write it down a little bit convoluted, but don't be scared about that. It's like you will never probably use that, but you just need to understand how everything is combined together, right? So you multiply your previous layer by the weights, and therefore your weights are actually, you have 1, 2, 3, 5, 1, 2, 3, 4, 5, 6 weights. It's basically number of layers here, 3 nodes multiplied by number of nodes in the first layer. So this is your total weight for layer number 2. And again, you also have this. Okay, for this layer, how many biases do I have? For this hidden layer in the middle, how many W0s do I have? 3, exactly. So because again, you have bias and you have I, and I is the number of the node in each particular in our current layer. So we have I equal 1, I equal 2, and I equal 3. Okay. So that's how we get linear combination. It's just simple linear combination. And then what we are doing, we apply our nonlinear activation function on the top of that. So again, let me repeat it again, maybe with the colors now. So what we have, let's take a look at this node number 1 in the second layer. So in order to get it, in this case, we will have this equal to 1. So we would like to take the bias, 0 it means bias, for the second layer when we are leaving, for the first node. And then what we want to sum, we want to actually, I will just open the sum here. We would like to take J is running, okay, what's the value of M in this case? This M, 2. We right now look through all neurons in the previous layer, right? So, and let's take a look at here, for instance. So we need to take this layer, we need to take this value, x1, 1, multiply it by some weight. Okay, how we determine the index of this weight? It's very simple. J is index where we come from. So basically, this would be 1. So we have 1. And I is index where we're actually going to. Again, in this case, we also have 1, right? And that's the first component. So and now, let's add what we need to add. X to 1, exactly. And we need to multiply it by the weight of this particular connection. So according to our rule, what would be the indexes? 1. No, not 1, 2. 2, 1. from second one, so this is the second one, to the first one. So we have 2, 1, and again, since they are living in the same layer we are calculating for, we have its indexed. So it's very, very kind of simple when you understand how in general it works. So then you add basically this particular selected activation function, and you are good. So if you look at basically TensorFlow, again, this is an example I show you already. All these layers are called dense layers. They're dense because they have a connection to all nodes on the right and all nodes on the left. So therefore, in order to actually build this particular model, we just need to say, okay, we will just do this in practice. So you open the model and then just describe layer by layer. So first layer, it's a dense layer with 2 nodes, this number 2, and with some activation. Like right now, we don't care about activation. Then next layer will actually, it's again dense layer, but with the 3 nodes. So that's how you do this. And then you have the final layer, basically your output layer, again dense with the 2 nodes only. It's very straightforward. That's why TensorFlow is very cool. Just write that, and you describe everything here. And when you do some training of the neural network, all these mathematical operations will be done automatically. So, and of course, you then have a next step. So right now we had all access here. We have all values in the hidden layer. And now I'm asking you what will be the output layer. And you are doing absolutely the same operation again, except right now you see basically instead of index 1, you have this layer 2. And instead of 2, you have a 3. And now my question, what will be the M prime value? Any other suggestions? What would be the value of M prime? 3, exactly, because we are looking for the 3 nodes in the previous layer. So quite straightforward. Question, we have this big system, and now let's assume that I ignore this activation function. I say my activation function is basically something like that. So we're saying that xy is equal to zy, so without any activation. So we completely skip that. So what will happen in your opinion? And okay, maybe on this particular network, it's not so clear, but let's say I have these 2 inputs, then I have 3 layers, 2 layers again, 3 layers, and they all, I don't want to connect everything, 2 layers, and we have 1 output. Yeah, so it's called deep neural network. It has a lot of hidden layers. They are all dense, and we have a lot of actually weights corresponding to that. Is it important in this case to make it so long if we completely ignore activation function? Oh, that's right, because not even like that, to be honest. Yeah, we can put them into one line in general, but if you have a linear combination of linear combinations, it's by definition is linear combination. That's a definition of linearity. So therefore, you can build whatever network you want, but at the end, it's just linear combination of your inputs. So really, you don't need to do that. So therefore, if you want to do something complex, you need to have activation function, and you need to do it smartly. So let's return to the previous problem. Now, we know these activation functions. We know that we can actually do some nonlinearity. And let's try to build a simple network that actually describes this particular picture. Let's start with a simplified problem. Let's start with the problem when I say, okay, everything below 5 for x2 is safe. And we kind of x1 we ignore right now. In this case, I have our perceptron here. What can I say about weight of x1 and weight of x2, in your opinion? Can I say something from the scratch, from the beginning? Can I have some conclusion? Can you do it to extreme? We don't care about x1. Really, x1 doesn't matter right now. Again, I assume that this is basically infinitely here. So x1 doesn't matter. So we ignore x1, and now we work only with x2. And now I have a question. Okay, we want right now to basically have a function from x2. Okay, let's do it even better. Let's say, okay, we have g of VW x2. Right now I will, okay, maybe plus b, something like that, plus bias, corresponding to, and I would like it to be, so what I would like this function to be, if our output is here. So I would like it to be 1 and 0 if failed, right? Now, when we know, right now, fortunately for us, we exactly know the solution of the problem. We see this particular plot. So now, basically, how can I reformulate knowing that we already know? Exactly. So we basically want to say, so if x2 is larger than 5, then we would like to have g equal to 0. If can we find, and now my question would be, first of all, what we will consider as our activation function in this case? We have a very, very nice output, 1 or 0. Which function we can use? Step, again. Right now, I simplify that we can use step function. So our g, in this case, our Heaviside function. Okay, so we basically have something like that. Let me just, in order not to... let's introduce a function of f, let's say, and we say Heaviside of our g function, right? Question now is the following. We need to find W2 and B. Any ideas how we can do that? Come again? Okay, what will be W2 in this case? Okay, let's do that step by step. It's not so easy, to be honest. It's not so easy to see. So what we know about Heaviside function, we know that Heaviside function of, let's say, some z is equal to, it's equal to 1 if z is more than 0, and Heaviside function of z is equal to 0 if z is less than 0. Okay, so now our z is our linear combination. So how we can express z through x2 in order to get this result? Go ahead. Okay, right. Yes, kind of. What we can say in this case, we can say, okay, let our argument would be in this case right? So in this case, if x2 is higher than 5, what we have? We have 1. And we have 0. What problem do we have now in comparison with what we want? Blue is 0, red is 1. Does this function work for our case? So can we say that G is equal to Heaviside of this linear combination with bias? Does it work? What's wrong? No, we ignore x1 right now. x1 doesn't matter. Okay, well, okay, I can say plus 0 x1 if you wish, because it's... What happened? Can I do Ctrl Z? Cannot. Okay. I will write it a bit again. So our... So right now we know that G x2 minus 5. Okay, I will add it for you. because, okay, if you want, I can add 1, multiply. And we know that it's actually heavy side. And we know that it's actually 1 if x2 is higher than 5, and 0 if it's lower. Do you see a problem? Okay, let's take a look at a plot. If x2 is equal to 10, what should we have? Do we have 0 now? Okay, we have 1. If x2 equal to 0, what should we have? 1. Do we have it? No. So how to fix that? Any ideas? Exactly. Just do invert the argument. So basically, our final function for that, we call it g2 because it depends on x2, would be equal to heavy side of 5 minus x. And that's all. So right now, we actually find the function g2 that describes this particular plot. Nice, really nice. So can we do very similar for x1 in this case? Let's consider another case when we have the left side green, safe side, and right side to be dangerous. What would be my function in this case? Let's call it g1. So what it will be equal to? Yeah, it's 2.5 here, but yeah, minus x1. So to be honest, let me make it, it's not g1 in particular, but yes, our sort of I1 that we are finding here would be equal to h. Cool, nice. So we actually learned to do that. But can we do it for this particular thing? Right now, we have an even more nonlinear system, but we already have some ideas how we can at least solve these first 2 steps. So we actually solved that one. So let's write our heaviside function basically here. So we have heaviside of 2.5 minus x1 and heaviside of 5 minus x2. And again, we are lucky and we are happy that we actually do know this cross dependency, because otherwise we cannot do that probably manually. Nice. So therefore, so we have equal, this value is 1 if x1 is less than 5, or 2.5, sorry, 2.5, and 0 if x1 more than 2.5. And here we have 1 if x2 is less than 5, and 0 if x2 more than 5. Right. And now I'm asking you what to do with these last things. So we need to take these values. It's our new axis. It's our new inputs, basically. Let's call it x1, 2, because let's say second layer, and x1, 2, I can write it inside, and x2, 2. And we right now need to do something like linear combination and then apply another function in order to get our output that we want. We want 1 if intact and 0 if failed. So basically, we want 1 here, and we would like 0 here, right? Yes, exactly. So that's really nice. So that's exactly what I want to write right now. So I want to write. So basically, we have 1 if x2 less than 5 and x1, yes, less than 2.5, and 0 otherwise. So technically speaking, what we can do, we can actually write this thing. If we have 1 and 1 here, say 1 and 1, so this would be 1x2, this would be 2, 2, and that would be our desired output. We would like to have 1, right? We would like to say that it's intact. If we have 1, 0, what do we have? 0. If we have 0, 1, 0, 0. Nice. How? What it reminds you probably? It's AND. Yes, it's a Boolean AND, but we cannot use Boolean AND because, like, how? We need to turn it into the proper mathematics. What would be your guess? What we can do with the, and I will give you a hint. Here we also will use Heaviside. Now I'm asking you, can you create a Heaviside from the combination of this x1 and x2 in order to get me 1 in this case, in the top case, and zeros everywhere else? Come again? That's a good approach. Unfortunately, it doesn't work like that. Because if you multiply x1 by x2, you don't have linear combination anymore. You have already polynomial things, and that doesn't work. You cannot multiply inputs. You can only combine them or multiply them by weights and then basically add them together. So that would be a good solution, but unfortunately, in this case, it doesn't work. So what would be another thought how to do that? It's kind of okay. What I have right now I have Z as some combination of W. Actually, quick question. If I would like to be plus B, of course, some B. If I would like to be quite precise, what indexes should I put here on the top of W1 and W2? 2, because it's a layer we are right now. No, it's not 2. No, it's 3 actually. It's 2. No, it's 2. No, it's actually 3. Because we're actually calculating the third one, right? It's 3. So, but for now, I ignore this one index. Okay, so we can only do that, and then we can apply Heaviside. So our y would be Heaviside of that. So any ideas what we can do here? How we can make this function? Okay, let's start with your suggestion. So you are proposing z to be equal. Give me a minus or plus? Minus 2, okay. What's your suggestion? 1 minus, okay, this is option number 2. Oh, sorry, z is equal 1 minus. Okay, and then you want to have a side on the top of that. So let's see if it works. So if x1 and x2 will be equal to 1, you get z equal to minus 1, right? In your option, z equal 1 minus x1 plus x2. If x1 is equal 1, x2 equal 2, you have 2, you have 1 minus 2, you have minus 1, and Heaviside from minus 1 will be 0, right? And we want 1. We want if x1 and x2 equal 1, we want 1. So your thing doesn't work. Your thing actually works almost perfect. Can you do a small adjustment in order to avoid the border case? What I would say. All right, so we will create another border case. Something between 1 and 2, minus 1.5. Because in this case, if x1 and x2 is equal to 1, you get 0.5 at the end, and your Heaviside is definitely 1. And if one of them at least 0, then you have definitely minus 0.5 or lower. And that's exactly how it works. Why 2 doesn't work? Because in this case, you really need to care about this equal sign. Where is it? Basically in the bottom condition or the top condition, and kind of it's better to do it's safe. Let's basically say 1.5. So at the end, actually, what we did right now, we actually build the function. We basically build everything, and now we can actually say that our output is equal to Heaviside from Heaviside of minus x plus 5. It was x2, sorry, plus Heaviside of minus x plus 0.25 minus this 1.5 that we introduced right now. And that's all. So right now, actually, this particular equation describes everything. It really describes everything. And now, if we put x1 and x2 in a blue zone, we will get 0. If we put them into the green zone, we will get 1. So that's exactly how technically neural networks work. So you really have these linear combinations with activation functions, usually not Heaviside, but again, for the sake of explanation, I would prefer to have Heaviside here that actually did everything. So now we have basically a neural network that can predict nonlinear shapes. And what do we know in this case? Like, I like this example. I really understand that you understand what happened. Do you have any questions regarding this particular example, how we build everything from the scratch? No? Cool. So basically what we know right now, we know that combination of the linear transformations and nonlinear activation functions can simulate complex input output mapping. So nonlinear input output mapping. And if you remember from the previous lecture, we had this nice equation when we can search for y, we can search for x, and sometimes we can actually search for f. Now what we are going to do, we searched for y. So, and we considered an ideal model and guessed the weights manually. So that's what we did. We know our output, we know everything, and we actually assume that we can manually guess the weights. So the most important thing in a neural network is the weights. So what we actually did during this time, we actually guessed the weights and biases. That was the most important part. We nothing else. So we just apply some activation function, but at the end, we search for W1 and W2. So problem that real models have much more input variables. And we don't have infinite amount of data as well. So usually I will show you that's not how it looks like. And usually we cannot actually nicely visualize output. What we did here, we say, okay, this area is 1, this area is 0. Or in the case of the stiffnesses, we actually basically put a color. We are lucky that we have only 2 variables. Usually you have, I don't know, 1,000 variables, and then you cannot do anything. The interconnection between variables might be very complex. Now we get lucky that we at first step can decouple x1 and x2, and the measurements outputs can be very noisy. And there are 2 definitions of noisy. Again, one is more or less Bayesian noise, and another that we have some inaccuracy in measurements. So we will actually not go into details here. So therefore we need a more universal approach for solving such problems. We cannot do it manually. And that's basically what neural networks usually provide. So what we actually do about our problem, we know about our problem, and actually how usually neural network problem looks like. So if we talk about the problem 1, we are aiming to find the total stiffness. Usually we don't have this nice map. We have a points, we have a measurement. So you basically combine some different springs and get these points. And the task is to find this neural network, this function, very complex function, that will actually, based on x1 and x2, nicely interpolate and explain this data. And in problem 2, we have a very similar thing, but in real measurements, what would we have? We would have basically some points here, and again, our task is to find this border here, to find the case when, basically, to find a function that we can separate green from the blue. And for both of these problems, we know inputs and outputs. That's very important. We know our stiffnesses of the springs, and we know the total, because we actually calculated that. Or in the case of real experiments, you just measured that. And in this case as well, so we know x1 and x2, and we know the output. Maybe not in all points, but at least in our data set, we know that. So it's called supervised learning. When we know labels, when we know inputs, we call it supervised learning. And this problem is called regression, because we have continuous value as output. And then this problem is called classification, because we try to classify our structure if it fails or if it's not failed. So what we do, what do we actually mean by saying we train neural network? So we're actually looking for the weights. And we obtain good values for the weights. So the algorithm in general to approach any problem that we solve is define the problem, identify input-output, because it's very important, decide on an architecture, decide on, okay, how many hidden layers we have, or do we go to the crazy architectures that basically do not use only dense layers, but something convolutional neural networks or something like that. We define train set. We actually pick some values that we really know that we'll use as a train set. We train our model, and that would be a discussion for the next classes. We will discuss what do we mean and how we do that in practice. We pick test set. That's very important because you can actually take 3 points and feed them with a 4th order polynomial or 10th order polynomial as is, but it will be absolutely useless because if you take another points, they will not work well. So that will be, we'll discuss it. It's called overfitting or underfitting. So then you evaluate your model. Basically, you want to say how good your model is, and that will be the next Monday. We'll talk about the measurements of how good your model is, how good your prediction are, and basically enjoy your good model. You put it in production, and you are happy, and everything is nice. So now a little bit of game, since we already defined supervised learning. It's a learning when we have inputs and output labels, so we know connection. And there is another type of unsupervised, of course, when we actually don't know output labels. So this particular neural network, when we look at the picture and try to basically understand if it's a cat or dog, so my first question, is it supervised or unsupervised? Come again? So, therefore? Usually it's supervised, yes. Regressional classification. Classification, again, we have classes. So it's usually a supervised system because we usually, how we train neural network, we show a neural network the picture of the cat and saying, this is a cat. We show the picture of the dog, say, this is a dog. And we show 1,000 pictures and everything fine. But in many, many cases, actually, what you can have is you can have unsupervised mode problem that looks like that. So you just show a picture without telling if it's cat or dog. A neural network will learn to separate the two entities. It will look at the ears, for instance, and say, okay, this bunch of pictures with the animals, these animals have the pointy ears, for instance. I have no idea if it's dog or cat, but this is a specific animal. This is one type of animal. And if you look at the other pictures and say, it's another type of animal. So basically, it separates different animals without labels. And if you remember from the last, basically, slide, we had last lesson, we had a very simple problem regarding that. So right now, since we're in mechanical engineering, we have a crack, supervised or unsupervised. Okay, let's first regressional classification. Safe or unsafe? The answer is basically we're trying to find. Classification, right. How can we make it regression? What question do we need to answer here in order to get regression? Come again? Yeah, in some, you kind of, yes, you can actually say that. You can say, okay, what's the length of the crack? So that would be regression. But also you can ask actually remaining lifetime. So basically, not only about the safe, if the system is safe or not, basically, how long should I wait before it fails? So is it, again, am I expect to basically live in this building for 10 years, or should I actually leave now? So remaining time would be actually, in this case, more or less regression problem. And actually, that's example from the previous lecture that I mentioned. So here, on this particular neural network, we actually have a very nice combination. So first, we have the system when it looks at the CT images and do lung region extraction. What do you think? Is it supervised or unsupervised learning? This first step. Do we have, basically the question, do we have a labels of output or not? When we do something like extraction, or if you actually see encoder and decoder thingy, it's a good sign that it's unsupervised. So basically, you actually do not train it like this is a cat, this is a dog. You're saying, okay, this is an images, find anomaly in images. Find something that actually kind of important in the image. And that's exactly its unsupervised thing. Then you actually have another unsupervised system. And here, classification, it's already had to be supervised because the doctors here, by looking at that, they basically assign specific, I don't know, illness to the specific image. So in this case, you have more or less supervised learning in this stage because you need to move it to the real domain when you really know what does it mean. Not only to look at the particular image, but also to understand what does it mean, and that's usually associated with more or less supervised learning. These examples of the structure generation, they're actually quite interesting because these first steps usually are supervised because you provide them with the labels. At the same time, generation step can be both supervised and unsupervised. So again, there is not very easy way to split them. In many neural network architectures, you actually have both of them. So, but in simple systems, you actually quite easy can say, okay, this is a classification regression, and this is, let's say, supervised or unsupervised system. So basically what we learned during the lecture, let me take a look at the, good timing, is that we can separate supervised learning. It's when output is labeled, and usually can be classified, in this case, the problem as a regression and classification. And we can actually separate unsupervised learning when output is not labeled. And here we can mention some types of machine learning as a feature learning. Basically, again, this things what happen with the lungs. After regression, and when you try to predict, let's say, financial things, so you are trying to guess a next movement of the market based on the previous data. And you also have the generative models that basically try to generate something. When you generate something, you definitely have no output because you don't know what you actually want to get. So that's basically the main things that you need to remember from this class, that basically we have supervised learning and unsupervised learning. And right now I would, do you have any questions regarding this material of this lecture? Okay. In this case, as I promised, we have a small paper walkthrough. I like this format a lot. Basically, right now, we'll take a look at the paper. And in 10 minutes, basically, briefly go through that and see how particular neural network or architecture has been used for real applications associated with civil or mechanical engineering. So, and this paper, I found it in the Journal of Engineering Structures. It's called Prediction of Seismic-Induced Structural Damage Using Artificial Neural Networks. It's quite old, it's 2009, but at the same time, it's really, really good because it's really easy to understand what happens. So now I will actually keep the inks, and I will open the small margins, this one. Okay, I need to do, give me a sec. This case, duplicate, keep changes. Okay, now you see everything. And now we take a look at this paper. Do you see a text? I will read some of that, but in general, do you see what's happening here? I will just scroll it down a little bit. So everything more or less visible, yeah, for you? I can zoom out a little bit, yeah, no problems. Something like that. Again, I will try to do that. Let me just take a look if I can do inks here, because this is important. Yes, actually, that's exactly what that's exactly what I probably will do right now. I have a version in PowerPoint as well, just for this particular reason. In PowerPoint, there is a little bit of issue because I cannot really probably write. Can I write in this particular mode? Oh yeah, I can. Okay, we will work in this case not in presentation mode. We'll work in this mode. Can I close it completely? Yes, I can. Good. Can I close this as well? So the paper, as I already mentioned, is called Prediction of Seismic-Induced Structural Damage Using Artificial Neural Network. So what authors are doing, they are saying that, are you familiar with the finite elements method? Do you know what is it? Basically, not quite very classical numerical methods, and probably you had a course on that. So authors from New Zealand saying that FIM is applicable when a small number of predetermined structures is to be assessed but become inefficient for largest for larger buildings. Seismic vulnerability curves enable damage estimation for classes or similar structures characterized by a small number of parameters, and typically use only one parameter to describe ground motion, so basically to describe earthquake. Hence, number of stories and the base or capture the full complexity of relationship between damage and seismic excitation parameters is hard. Oh yeah, I missed this. Sorry. Hence, they are unable to extend damage prognosis to wider classes of structures, for example, buildings with a different number of stories and base, or capture the full complexity of the relationship between damage and seismic excitation parameters. Motivated by these shortcomings, this study presents a general method for predicting seismic-induced damage using artificial neural networks. So basically, what they are saying that right now there is multiple ways to assess and predict damage due to earthquake, and you can do it using nonlinear finite elements, as you can see here. But also there is so-called vulnerability curve. It's basically usually it looks like that. So here you have your, let's say, earthquake. That is correct, yeah. Let's say power, I would say, something like that. And here you have the probability of sort of damage, or you can also say that you have here this damage parameter, what they call. And usually it looks like that. Usually all these curves looks like that. So when your earthquake is not so powerful, you basically have sort of nothing. You are not damaged. When it's very powerful, actually doesn't matter how powerful is it. It's actually doing this more or less the same result at the end. So it's usual curves. And unfortunately, authors say, however, if the assessment is required for numerous structures and process becomes time-consuming and inefficient, these curves provide a more efficient methods for predicting damage to a class of similar structures. They are generally constructed based on the statistical analysis or historical records. Unfortunately, they use only one parameter usually to describe ground motion. Earthquakes are extremely hard to describe. So, of course, for simplification, what you usually can look at that is like basically maximum acceleration or something similar. So, and unfortunately, again, all models before that worked only with the simple parameters. And these shortcomings become particularly important as studies have shown that correlation between damage and the parameter describing ground motion are very complex. This is exactly the good recipe to go and try do machine learning, because as we discussed, complex interaction between the inputs and outputs, it's exactly the field for machine learning in neural networks. Parameters describing ground motion are very complex, and the set of such parameters rather than one index would be necessary to capture the relationships. Here what they're saying that it's not enough to look at the one parameter of the earthquake, you really need to look at the multiple parameters. And therefore all these curves would not work very well, because yes, they usually depend only on one parameter. So what they're doing in this case, they're saying, okay, a tool that is often used to describe complex relationships influenced by numerous parameters are artificial neural networks. Although they have been applied widely through the civil engineering and structural health monitoring fields, their use for seismic damage prediction has been limited. So, and actually they discuss, as usual in literature, in scientific literature, they discuss some examples, and I like this example that some guy studied how the churches basically collapsed during the earthquake. So the church was broken into different structural components: facade, sidewalls, spire, and these components and the arrangement were used as input of neural network. So basically the paper that they're mentioning, this paper took different parts of the building, combined them together, and basically depending on the sizes or depending on the geometry of this part, you kind of have a different buildings, and then you try to train neural network to predict how it will collapse and when it will collapse. However, they say that's not enough, and they want to contribute more. And they say in this study, a method for predicting seismic-induced damage using ANNs is proposed that can be applied to a wider class of structures. And they look at the 2D reinforced concrete frames. Basically, they simulate the building as a reinforced structure, and that vary it in topology, stiffness, strength, and damping. So multiple parameters of output, like buildings are very buildings are very complex in their system, and they were subjected to a suite of ground motions characterized by peak ground acceleration, peak ground velocity, and peak ground displacement. So already 3 parameters, and then they put more. They say spectrum intensity and dominant frequency and duration. So they try to make the earthquake more complex than before. And what they did then, they get so they say, okay, we have this very strange, very complex connection between input data, that in this case geometry building, geometry of the building, sorry, and earthquake parameters, and output is basically if this building will collapse or not. So, and they say, okay, artificial neural networks are absolutely perfect for that. So, and they describe a little bit of theory, and in this theory you actually see exactly what we saw today. They just denote it differently. You say that input, it's V, and weights are Z for some reason, and this activation function is F. Again, exactly what we did today. Then they basically assess the accuracy that we will do next Monday. Say, okay, that's a difference between the real values and predicted values. And then estimate this is basically one number, how good your match between your predictions and real data are. So, and in the training phase, what I mentioned before, an input selected from a set of known input-output pairs is supplied, and the network calculates the output from the given input. The error between the desired and actual output is then propagated backwards from the output layer to the preceding layer, hence the name of backpropagation algorithm. We will talk about it later, but that's a way to train neural network. You need to find the weights, and in order to do that, you need to have the backpropagation method. But at the end, what they're doing, they have inputs and try to predict outputs. So they use some way to avoid overfitting. That's what I mentioned again. When you train neural network, you need to be very careful how you do that, because you may have a problem when it predicts very well on the trained data set, but will absolutely fail on the real data set. So they actually account for that. And what they did, they basically run finite element simulations. For the different combinations, they choose as 90 parameters input, basically 13 structural parameters and 6 parameters from the ground motion. I will not list all of them, but here you can see them. And again, this is the parameters for the ground motion. And to ensure the network learned the combination of the parameters that cause damage, 9 earthquake records were used to build the data set. The properties of these earthquakes are given in table 3. So they basically looked at the historical data, the historical earthquakes, and they replicate them in finite elements and see how it affected the buildings. So, and this is important point here. With the scarcity of complete and accurate historical data, the data sets used in the simulations were produced from the results of simulations. So, of course, it's better to go into real world and do real experiments, but unfortunately in earthquakes it doesn't work like that. You need to look at the historic data, and there are not a lot of them. So there are not a lot of these input-output pairs. So what they did, they actually did their finite elements first, and then they assess damage criteria. So basically this is criteria from damage index, that range from 0 to 1, and 0 means our building is absolutely okay, and 1 means that it's actually quite failed. From that generation procedure, they obtained the data, and what they did, that they actually trained neural network. This pink paragraph says that we train neural network. They did it in a little bit weird manner, to be honest. I found it a little bit weird. So what they did, they built a very simple neural network, very similar to what we did today, of course, with more nodes and more inputs and more hidden layers. Actually, no. In some cases, they used a single hidden layer, so it was very, very similar to what we did today. But for some reason, they trained each neural network 50 times, because actually your result may depend on initial guesses. So in order to avoid that, they actually did 50 different sets of guesses of the weights, and they get different results, and they pick the best one. So this is a little bit unusual, to be honest, approach, if I understand correctly. So because right now there are more robust methods for weight initialization. So in TensorFlow in particular, there are already existing procedures how to do weight initialization in a proper manner. So probably in 2009 it was much harder. So they decided, okay, we'll run 50 different initial conditions and see what we'll have. And then they actually trained a model. And here you actually you see the prediction between the damage predicted by artificial neural network and the damage predicted by finite elements simulations, finite elements modeling. And this is super classical scatter plot you will see everywhere. So what's the best you can get? How the best predictions will look like, in your opinion? Yeah, everything will be exactly on 45-degree line. So everything will be exactly the same as predicted by finite elements. But again, this is a dream. We actually had that in our model. We had that because we predict exactly if our system is safe or not safe with the springs. But of course, in reality, you never have that perfect fit. So, but this fit is actually quite good. So especially for the for the low damage, they claim very, very good fit, and I agree with them. And actually here you see on the left the table saying that if this damage index is less than 0.11, so no damage, and if its damage is more 0.77, that means that the system is collapsed. And you actually see that in this collapsed region, it's much harder to predict accurately because you have less points, and probably it's more nonlinear than in the lower regime. So what they did next, they did a very smart thing. So they say, okay, one of the strengths of this artificial neural network is ability to use the relationship for the data that have been unseen by the system yet. So what they did, they built new buildings in simulations, and they decided not to run the finite elements, and they just give already these buildings, these geometrical parameters and the earthquake parameters to the system that's already trained and see what it have predicted. And actually, prediction was not so bad. So in the new building, the 4-store buildings with, I don't know what does mean 3-bay frame, they have a very good match. So that actually illustrates that your model works correctly if you can apply it for the unseen data. So the fact that you have a perfect fit for the data in training data set doesn't mean anything. Because you can take the polynomial of the, I don't know, of order 100, and you have 99 points, and you will have perfect fit. Your line will be exactly 45 degrees. But then again, you have another point, and everything is collapsing because it doesn't make sense to fit like that. So the fact that they did this for unknown buildings shows that their model works. And this is actually very good. And they say, okay, nice, everything is nice. But what they did next, actually, they say, give me a sec. Where was this one? And this one, I really like this one. In the third example, the neural network was used to predict damage in all frame, but caused by previously unseen earthquake. I was actually a little bit wrong saying that they put absolutely unknown motions. No, they use the same earthquake but change the geometry of the buildings to unseen one. But now they say, okay, now what will happen with our model if we just replace earthquakes and just use the data from earthquake that was not seen by the model yet? And they did that. You see, they use this particular earthquake, and where is the plot? And the plot is here. And you actually kind of see here that the prediction right now is not so good. So that means that their model generalized very well for the unseen buildings, but unfortunately has some problems in generalizing for unseen earthquakes. So, and what I like about the conclusion, they're saying the errors between FIM and end results were on average acceptable, but a relatively large number of significantly different damage predictions could be also observed. The case of prediction for a previously unseen earthquake proved to be particularly challenging in this respect. It's really nice to have this honest assessment of the model. They showed that this model generalized well for new buildings, but it actually fails to generalize for the earthquake, and they do not try to hide it. And the NNN has been demonstrated to interpolate the Lorentz relationship within the range, but any extension will require the generation of additional training data over an appropriate expanding parameter range. They also kind of understand the limitations of the data. So if you go to a very high buildings, for instance, or buildings with a very complex geometries, architecture, probably their model will not work very well. So, and at the last sentence, they're saying the potential drawback of the approach is the generation of data sets, which is time-consuming and more efficient ways of generating training data will need to be investigated. Basically, what they did, they used nonlinear finite elements, and it's kind of hard and it's very expensive computationally. So they looking for a new way to do that faster. But again, I don't know if they succeed in that or not. But what I really find a little bit strange and untypical for scientific literature, usually your last sentence should be positive. You're saying, okay, with this approach, we will help humanity or something like that, of course, on a small scale. The fact that they put the negative last sentence, it's really interesting and quite not typical for the scientific literature in general. So that's basically a story of this particular paper from the New Zealand. And if you have any questions, regarding this basically walkthrough, I will be really happy to to answer that. Do you have any questions, any suggestions about this particular paper? Do you find it quite... Come again? I have no idea. I need to check. It will be interesting to check, to be honest. I found this paper is very, very good because they used very simple architecture, and I think you can understand what they did. Did you grasp what they did in general? So in this artificial neural network for these earthquake predictions? This is nice. So do you have any other questions regarding this paper, or maybe neural networks in general? Do you find this particular walkthrough through the papers interesting? Good. Because gradually we go to more and more advanced. Right now we don't have enough experience to go there, but with the lectures, we'll talk about training, we'll talk about more complex and advanced architectures. So we will be able to look at the not more interesting, but different types of papers. So I think on that, I would like to end this particular lecture, and thank you for being here. And yeah, see you on Thursday. Good. Yes, paper will be. Next time I would probably even share another paper before class in order for you to maybe. Yeah. Again, it was a little bit late to do. Oh yeah.